Hi everyone, I'm Angelina.
I'm Audrey.
I'm Gia.
I'm Audia.
And I'm Ezra. Our project is called Planes and Planes.
So we're going to be investigating a real-life plane crash that happened in 1956 and using some Calc 3 concepts to theorize and potentially try and visualize ways that the collision could have been avoided.
Let's get into it.
On June 30th, 1956, Trans World Airlines Flight 2 and United Airlines Flight 718 collided above the Grand Canyon, resulting in what was at the time the deadliest civilian plane crash. Both flights were delayed, with the TWA flight departing from LA International Airport at 9:01 a.m. and the United Airlines flight departing from the same airport at 9:04 a.m. Their flight plans were completely different, with the TWA flight intended to fly at an altitude of 19,000 feet at a speed of 270 knots, while the United Airlines flight was intended to fly at an altitude of 21,000 feet at a speed of 288 knots. However, the TWA flight hit some turbulence and gained clearance to fly 1,000 feet above any unfavorable weather. But soon following this, contact was lost with both planes, and from the investigation, it was concluded that the two planes collided at an altitude of 21,000 feet, because the pilots deviated from their original flight plan to provide their passengers with a more scenic view of the Grand Canyon. That day, all 128 people on board passed away, changing air traffic management forever. This leads us to the question, how could this collision have been avoided?
Hi, I'm Audia, and I'm going to be discussing how skew lines in planes could be used to model the plane pad's intersection and how that potential situation could have also been avoided. So let's get into the math. If we consider arbitrary parametric equations for the plane, we may understand the potential for a crash in a better sense. If we assume the airport, Los Angeles International Airport in this case, to represent the origin, the plane's starting positions can be imagined slightly further from the building owing to things like runway distances. In this scenario, plane 1's starting position can be 230 and plane 2's can be 120, 18, 0. Z remains 0 in both cases as we initially remain grounded. Take plane 1 to have the following parametric equations. X equals 2 plus 8t1, y equals 3 plus 10t1, and z equals 38.9t1. Take plane 2 to have the following parametric equations. X equals 120 plus 3t2, y equals 18 plus 5t2, and z equals 20t2. To solve, we would set up a system of equations. To do this, we would first equate the x equations of both plane 1 and plane 2 to get 2 plus 8t1 equals 120 plus 3t2. We would then equate the y equations of plane 1 and plane 2 to get 3 plus 10t1 equals 18 plus 5t2. Now, there are many different ways to solve this, but the way that I'll do now is multiplying the top equation by 10 and multiplying the bottom equation by negative 8. Doing this allows us to get rid of t1 as a variable and allows us to just solve for t2. Solving for t2 alone gets us that t2 equals 106. Using t2 equals 106, we can plug back into one of the initial equations and get that t1 equals 54.5. By themselves, the values don't prove anything. However, when we test T1 and T2 for our position of Z after equating the Z of plane 1 and plane 2, we find that the equation for Z is also satisfied, proving that an intersection will take place. If the Z condition wasn't satisfied, we would call the plane pads skew, meaning that they fail to intersect but are also not parallel, primarily because they may exist on different planes. This, in context, would occur if the plane pads remained at different altitudes. In the incident, Captain Shirley, piloting the United Airlines Flight 718, rose to an altitude of 21,000 feet. Shortly after, to avoid storm clouds, Captain Gandy, piloting the Trans World Airlines Flight 2, rose an additional 1,000 feet to incidentally end up at the same altitude of 21,000 feet. In a simple grasp of the issue, both airplanes began to occupy the same Z-plane, resulting in a problem. Lines occupying the same plane must either intersect at some point or be parallel. Since the plane's path couldn't be considered parallel, an intersection was unavoidable. In a simplified mathematical sense, if Captain Gandy increased his altitude to 23,000 feet, for example, the flight paths could be considered skew. Even if they passed the same x and y coordinates simultaneously, their z coordinates would differ, and the crash could have been avoided.
Hi, I'm Audrey, and I will be discussing a bit how we can use vectors and the dot product to model the 1956 Grand Canyon mid-air collision. We can model the collision of the airplanes in terms of vectors by using the dot product to determine the angle that the airplanes collided at. At the time of collision, the airplanes were at the same altitude of 21,000 feet, so we can represent this by making the z-coordinate of each of the airplanes' vectors 21. If we assign arbitrary values to the x and y coordinates that represent the airplanes' relative positions along the x and y planes, we can divide the dot product of the two airplane vectors by the product of their magnitudes to determine the angle at which they collided. Assume the vector coordinates of the two airplanes are as follows. Airplane 1 vector is 2, 2, 21, and airplane 2 vector is 12, 2, 21. In order to find the angle at which these two airplanes will collide, we will use the following equation. A dot B equals the magnitude of A times the magnitude of B times cosine theta. We can assume that A corresponds to the first plane's vector and B corresponds to the second plane's vector. First, we have to find the dot product of the two vectors using the following equation. A dot B equals A1 B1 plus A2 B2 plus A3 B3. If we plug in the numbers, we get 2 times 12 plus 2 times 2 plus 21 times 21, which equals 469. Then we have to find the magnitudes of each of the vectors using the following equations. The magnitude of A equals the square root of A1 squared plus A2 squared plus A3 squared. The magnitude of B equals the square root of B1 squared plus B2 squared plus B3 squared. If we plug in the numbers, we get the magnitude of A equals the square root of 2 squared plus 2 squared plus 21 squared, which equals 21.1896. And the magnitude of B equals the square root of 12 squared plus 2 squared plus 21 squared, which equals 24.2693. Then we have to multiply the two magnitudes together, which gives us 514.2568. Then we have to divide the dot product by the product of the magnitudes. 469 divided by 514.2568 equals 0.912. Lastly, we have to plug this value back into our original equation. 0.912 equals cosine theta, inverse cosine of 0.912 equals theta, and theta equals 24.217 degrees. The actual angle in which the airplanes in the 1956 Grand Canyon mid-air collision collided at was around 25 degrees. Therefore, our model uses vectors to represent the angle between the airplanes at the time of collision. The interference of other vectors, such as wind vectors, with the vectors of either of the two airplanes could have effectively prevented collision by altering the coordinates and therefore the angle between them.
Hi guys, I'm Gia and I'm going to be using parametric equations and space curves to examine a really interesting way of preventing the collision.
For a less realistic but still mathematically interesting idea, the two planes from the Grand Canyon collision could take two very different flight paths to avoid a crash. While this example is technically impractical, it is another way to avoid collision using concepts we learned in class. So the plane's new hypothetical positions are shown by the parametric equations shown here. Okay, so let's take a look at this problem. Two curves intersect when their position vectors are equal to each other or when their coordinates match the same t. So we can set 0, 5t, and 50 equal to 100 cosine t, 5t, and 100 sine t plus 50, which then is going to give us 0 equals 100 cosine t, 5t equals 5t, and 50 equals 100 sine t plus 50. The second equation right here is always true. So the question reduces down to whether the first and third equations can be satisfied at the same time. The x component gives us cosine t equals 0, which happens at pi over 2, 3 pi over 2, etc., while the z component gives sine t equals 0, and that's going to happen at t equals 0, pi, 2 pi, and on and on. But we can see here that there's no single value of t that satisfies both conditions at the same time. This means that the two planes are never going to occupy the same position, so they never intersect. So now let's talk about the shape that this graph might take on. Geometrically, plane A moves along the y-axis, or parallel to it, at z equals 50, which places it right at the middle of the helix created by the other plane. At t equals 0, we get 0, 0, 50. And at t equals 1, we get the points 0, 5, 50. And at t equals 2, we get 0, 10, and 50. So this produces a vertical line that's parallel to the y-axis, but is way above the origin. Now, for plane B, that follows a helix that wraps around the y-axis with a radius of 100 kilometers. Its projection onto the xz plane is a circle centered at 0, 50, and it rises at the same rate as plane A along the equation y equals 5t. The result is that a spiral is winding upwards along the y-axis, even though it never crosses the vertical line of plane A's path. Even when their y-coordinates match, the horizontal separation between the two planes, or basically the radius of the outer helix, ensures that there's not going to be any collision between the two. As t increases, the helix moves upward along the y at a steady rate of y equals 5t while it's moving in a spiral in the x and z. Plane A, of course, still remains a straight line through the center of the spiral, and the helix winds counterclockwise. This is important to note when it's going to be viewed from above, because sine t increases before cosine in z. And these two paths are entirely separate, and they're never going to intersect. Okay, so here we see plane B's spiral pattern with a radius of 100 and swooping around the path of the other plane, which has an elevation of 50 on the z-axis. There's also a little cliff on the side of the image of the graph, which is supposed to be representative of the Grand Canyon and kind of show off how this really weird flight path might play out in real life if we really had to make it that way for whatever reason. But yeah, that's just a really quirky, fun example of another way the planes might have been able to avoid collision. Hope you enjoyed.